The variance of the heteroscedastic estimates are given here. Variance of least square estimates, variance of least square estimates in the presence of heteroscedasticity is explained in this section. Before explaining the variance of least square in heteroscedasticity, a review of homoscedastic variance of least square estimates when the homoscedasticity assumption is followed is explained here. We have already seen that variance of beta 2 cap equal to sigma square by sigma xi square. Then variance of beta 2 cap it is defined as expected value of beta 2 cap minus expected value of beta 2 cap the whole square. Here this expected value of beta 2 cap is equal to beta 2. Then this can be written as expected value of beta 2 cap minus beta 2 cap beta 2 the whole square. That here we substituted this beta 2 cap minus beta 2 by this formula, that is expected value of beta 2 cap equal to sigma xi by a by sigma xi square, this which is equal to sigma k by I. Then substitute y equal to beta 1 plus beta 2 xi plus ui, then multiply with this, then we will get the equation beta 2 cap minus beta 2 equal to sigma ki square. Then this can be written as expected value of sigma ki ui the whole square. This can be expanded as expected value of k1 square u1 square k2 square u2 square plus kn square un square to 2 k1 k2 u1 u2 to 2 kn minus 1 kn un minus 1 un, and apply the assumptions. Expected value of ui uj equal to 0 in this equation. The remaining portion we will get is the expected value of ui square equal to sigma square, or we can say this equal to expected value of sigma ki ui square. Then expected value of this can be written as sigma ki into expected value of ui square. This expected value of ui square is sigma square. Then this can be written as sigma square and sigma ki square. Sigma ki square equal to 1 by sigma square. Then the variance equal to sigma square by sigma xi square. This is the variance of least square estimators when the homoscedasticity assumption is followed. Now let us see the variance of the estimates when heteroscedastic variance assumption is followed, or heteroscedastic variance are explained here. Variance of beta 2 cap equal to expected value beta 2 cap minus expected value beta 2 cap the whole square. This can be written like this, and finally we will get this equation the same way, and this can be explained as like this. And here this can be variance of beta 2 cap equal to the k1 square sigma 1 square k2 plus k2 square sigma 2 square plus kn square sigma n square. Since here heteroscedastic variance is followed, expected value of ui square equal to sigma I square. Then variance of beta 2 cap equal to sigma of ki square into sigma I square. Then this can be written as ki equal to xi by sigma xi square. Then this ki square equal to sigma of xi by sigma xi square the whole square into sigma I square. This can be written as sigma xi square sigma square divided by sigma xi square the whole square. This is the variance of least square estimators when the heteroscedasticity problem is present. Here another method of estimation of the OLS estimators when heteroscedasticity is present is explained. That is the method of generalized least square. That is the generalized least square method GLS. That is, in the presence of heteroscedasticity, OLS estimators are not blue. Or another method, that is GLS, that is generalized least square method, is usually followed. Make the parameter estimates blue in the presence of heteroscedasticity. That is, the GLS makes the parameter estimates blue in the presence of heteroscedasticity. Observations coming from the population with greater variability are given lesser weights than those from the population with smaller variance. The technique used here is that those who have higher variance are given lesser weights, and those who have lesser variance are given higher weights. And in the OLS method we cannot follow this strategy, and in this GLS method we can use this weighting method in accordance with the variability. That is, here in the generalized least square method we transform the original variable which will satisfy the OLS assumptions. That is, the original variable is transformed This can be explained as follows. Consider ya equal to beta 1 plus beta 2 xi plus ui. Then this can be written as ya equal to beta 1 x0 I plus beta 2 xt plus ut. Here we introduced the variable x0 I. Here x0 I equal to 1. That is the assumption. This is only an algebraic manipulation. Suppose that heteroscedastic variance sigma I square are known. Then we know the heteroscedastic variance, and dividing the equation 2 by sigma, that is simply divide this equation by sigma I, which will give the equation as ya by sigma I, that equal to beta 1 x0 I by sigma I plus beta 2 xi by sigma I plus ui by sigma I. Then this can be transformed as ya star. Ya star is nothing but ya by sigma I, beta 1 into x0 I star beta 2 star xi star ui star. That is, starred or transformed variables are the original variable divided by the sigma I. And here the variance of the term variance ui equal to the expected value of ui by sigma I square. The sigma ui by sigma I the whole square, that is 1 by sigma square into expected value of ui square, that is 1 by sigma I square into sigma I square. This equal to 1, which is a constant, that is transformed variance is homoscedastic. That is the technique used here. That is variance of ui star equal to expected value of ui square, that is equal to the expected value of ui divided by sigma I the whole square. Here this can be written as 1 by sigma I square into expected value of ui square. The expected value of ui square equal to sigma I square. That is sigma I square by sigma I square is equal to 1, which is a constant, and therefore the transformed variable has the homoscedastic variance. If we apply the equation to the Euler's, we produce the estimators. That is, if we apply the Euler's to this equation, then the estimates that we obtained will be blue. This procedure of transforming the original variable in such a way that transformed variable satisfies the assumption of classical model and then applying the Euler's to them is known as the method of generalized least square. That is, the procedure of transforming the original variable in such a way that transformed variable satisfies the assumption of classical model. Then apply the Euler's. GLS is Euler's on the transformed variable that satisfy the standard least square assumptions. The estimators thus obtained are known as GLS estimators. These estimators are blue. This is the GLS estimates. The derivation of the estimates of GLS equations are given here. We know that the equation is ya equal to beta 1 plus beta 2 xi plus ui. This can be transformed as ya equal to beta 1 x0 I plus beta 2 xi plus ui, where x0 I equal to 1, and then this divide the whole equation by the heteroscedastic variance sigma I. Then this can be written as ya star equal to beta 1 star x0 I star plus beta 2 star xi star plus ui star. Then ui cap star equal to sigma ui cap star equal to ya star minus, that is the steps are same as the Euler's estimators. Ya star minus beta 1 star x0 I star minus beta 2 star xi star. Then minimize the given equation on the least square criterion, and then the minimization is here ui cap star means ui cap by sigma I the whole square. Then this ya star is ya by sigma I, this is the whole square. Whereas the weighted least square method minimizes the weighted residual sum of square. Here we are minimizing the weighted residual sum of square, not the residual sum of square. Here we have a weight. Weight is 1 by sigma I. Then that can be written as, that weight can be written as wi. Then this equation can be written as sigma wi ui cap. The remaining portion is ui cap. Then that equal to, here the weight is 1 by sigma I, that is sigma wi into yi minus beta 1 star, beta 1 cap star minus beta 2 cap star xi the whole square. That is, the weights are inversely proportional to the variance of ui over yi conditional upon the given xi. It is b variant, that is variance of ui given xi equal to variance of yi given xi equal to sigma I square. Then differentiate the above equation with respect to beta 1, beta 2 cap. The procedures are the same. The normal equation will get like this, sigma wi by a equal to the same way. Here there will be one weight. In the earlier equation it was beta 1 cap only. Here there will be a weight. Then from that we can derive the estimates, that is beta 1 cap star equal to y bar minus beta 2 cap star x bar, and beta 2 cap star equal to sigma wi into sigma wi xi by I minus sigma wi xi into sigma wi yi divided by sigma wi into sigma wi xi square minus sigma wi xi the whole square, where y bar equal to sigma wi yi by sigma wi. That is, it is the weighted average. Then variance is defined as sigma wi divided by sigma wi into sigma wi xi square minus sigma wi xi the whole square. The difference between OLS and GLS is that in OLS we minimizes this residual sum of square, whereas in the GLS we minimizes the weighted residual sum of square. And since we minimizes the weighted residual sum of squares, the weighted least square, the estimators thus obtained are known as weighted least square estimators. That is the difference. In the OLS we minimizes the residual sum of squares. Here we minimizes the weighted residual sum of squares, and therefore the estimates are known as weighted least square estimators. This about the GLS method. In this section, we will discuss the method of detection of the heteroscedasticity. The important detection methods. The detection methods of heteroscedasticity can be divided into two. They are informal method and formal method. Informal methods mainly includes the graphical method, and the formal methods include Park test, Glaser test, Spearman rank correlation test, Golfet coin test, Bruce-Bagan test, White's general test, etc. Let us see the first one, that is informal method. The first one is the nature of problem. Sometimes the nature of problem itself will suggest whether heteroscedasticity is present or not. That is based on the a priori information. If no a priori information or empirical information about the nature of the heteroscedasticity is not available, then we can use the graphical method. Then another method is the graphical method. Do the regression analysis, obtain the residual term, and see whether it follows any systematic pattern. In this, we have 5 different types of graphical representation of the error terms. Here, UI caps are plotted against the yi cap. In the figure A, we see that there is no systematic pattern. There is no systematic pattern between the two variables. That is, it suggests that no heteroscedasticity is present in the data. From figure B to E, it exhibits a systematic pattern. Therefore, we can see that it is heteroscedastic. This is the another method for detecting the heteroscedasticity. That is, do the regression analysis, obtain the error term, plot the error term. If it follows any systematic pattern like these 4 graphs, then there is heteroscedasticity. If it is not showing any systematic pattern, then it is not heteroscedastic. Then some of the other methods are explained here. They are known as the formal test. The first one is the Park test. Park formalizes the graphical method by suggesting that sigma I square is some function of the explanatory variable xi. That is, here the heteroscedastic variance is defined as follows in the Park test. Sigma I square equal to sigma square into xi raised to beta e raised to vi. And this nonlinear form can be transformed into linear form by taking the natural log, that is ln sigma I square equal to ln sigma plus beta. That is here xi beta raised to beta can be written as beta ln x plus the e raised to vi. The natural log is vi. Then this can be written as alpha plus beta ln x plus vi, where vi is the stochastic disturbance term. In this equation, that is here we ln ui cap square equal to ln sigma square plus beta ln x plus vi. This can be written as alpha plus beta ln x plus vi. If beta here in this equation, if beta turns out to be statistically significant, then it would suggest that heteroscedasticity is present. If beta is statistically significant, then there is heteroscedasticity. If it is insignificant, then it is homoscedastic. That is, it is a two-stage procedure. That is, in the first stage we run the Euler's regression disregarding the heteroscedasticity question, then obtain the UI cap from the regression, and then in the second stage run this equation. Though it is empirically very feasible or appealing, it has some problem. It is argued that this error term EI may not satisfy the Euler's assumption. It itself may be heteroscedastic. This is one of the important assumptions against the Park test. It was raised by Goldfeld and Quant. That is, this beta turns out to be statistically significant, then heteroscedastic. If it is not significant, then homoscedastic. That is, it is a two-stage procedure. Run Euler's without considering the heteroscedasticity, obtain UI cap square, then run the regression like this. Then second method is the Glaser test. It is similar to the Park test. After obtaining the UI cap from the Euler's regression, Glaser suggests that regress the absolute value of UI cap on xi variable. That is, here instead of in the Park test we regressed the original variable. Here we regress the absolute value of UI, that is UI cap, the absolute value equal to beta 1 plus beta 2 xi plus vi. And he has given the following functional form also for explaining the test. That is, here the variable or independent variable can take different functional forms. This also as an empirical or practical matter, one can use the Glaser approach, but this was also criticized by the Goldfeld and Quandet, especially with respect to this error term, and they commented that it is serially correlated and it is heteroscedastic. And here this now the second criticism is that it is in non-linear form and it cannot be estimated with the usual Euler's assumption. That is, one of the important assumption of the classical linear regression model is that this parameter should be linear. If it is in this square root form, it is not linear, it is non-linear, and therefore we cannot apply the Euler's. Then next step is next test is the Spearman's rank correlation test. Here the Spearman's rank correlation test is defined as Spearman rank correlation is denoted as RS, that equal to 1 minus 6 into sigma di square divided by n into n square minus 1, given the model y equal to beta 0 plus beta 1 xi plus ui. Then fit the regression to the data on y and x and obtain the residual. That is the first step. Then second one, ignoring the sign of ui cap, that is, take the absolute value of ui cap and rank both ui cap and xi or yi cap according to the ascending or descending order and compute the Spearman rank correlation coefficient. Here the step is given this model, then regress the equation, obtain the residual, then take the absolute value and then rank both ui cap and xi according to ascending or descending order and compute the Spearman's rank correlation coefficient given in this equation. Assuming that the population rank correlation coefficient is sigma s, it is 0 and its significance can be tested as t equal to RS, that is Spearman rank correlation coefficient, the estimated value into root of n minus 2 divided by 1 minus the Spearman's rank correlation, the square. If the computed t-value exceeds the critical t-value, accept the hypothesis of heteroscedasticity, otherwise reject it. If the regression model involves more than one x variable, RS can be, or the Spearman's rank correlation can be computed between ui cap and each xi variable separately and test the model separately. That is, here we are ranking the residual as well as the independent for testing the significance. The next important test is the Goldfeld-Quant test. If According to them, if one assume the heteroscedastic variance sigma I square is positively related to one of the explanatory variable in the regression model, that is yi equal to beta 1 plus x2 I plus ui. Suppose sigma I square is positively related to xi, that is sigma I square equal to sigma square into xi the whole square, xi square, but sigma square is a constant. Then order or rank the observation according to the value of xi beginning with the lowest value. Omit the central observation where C is the specified a priori and divide the remaining by n minus C observation into two groups. Omit the central variable where C is the specified as a priori and divide the remaining n minus C observation into two groups, that is n minus C by 2 observation. Then do the Euler's regression on these two separate groups and obtain the residual sum of squares RSS1 and RSS2. RSS1 representing the RSS from the RSS from the regression corresponding to the smaller xi. That is, we ranked in accordance with the lowest value at the beginning and the highest value in the later stage or by the end or in the second portion. RSS2 that from the larger xi values, these RSS each have its own degrees of freedom, that is lambda equal to RSS2 by degrees of freedom divided by RSS1 by degrees of freedom. If ui are assumed to be normally distributed and if the assumption of homoscedasticity is valid, then it can be shown that lambda follows the F distribution with numerator and denominator degrees of freedom as n minus c minus 2k divided by 2. If the computed lambda equal to f is greater than the critical f at the chosen level of significance, we can reject the hypothesis of homoscedasticity. There is heteroscedasticity. And the success of this test depends on the number of central observations to be omitted and identifying the correct x variables with which to order the observations. Here we obtained two residuals RSS1 and RSS2. In the next stage, these two RSS1 and RSS2 each have n minus 3 by 2 minus k degrees of freedom or n minus c minus 2k by 2 degrees of freedom, where k is the number of parameters to be estimated including the intercept. For the two variable case, k is 2. Then compute in the stage 4 or in the next step, compute lambda equal to RSS2 by degrees of freedom divided by RSS1 by degrees of freedom. Then if ui are assumed to be normally distributed and if the assumption of homoscedasticity is valid, then it can be shown that lambda follows the F distribution with the numerator and denominator degrees of freedom each of n minus c minus 2k by 2. If the computed lambda equal to f is greater than the critical f at the chosen level of significance, we can reject the hypothesis of homoscedasticity. This is the assumption, or this is the Goldfeld quant test. Here the step is y equal to beta 1 plus beta 2 xi plus ui. Then suppose that here xi is positively related to sigma I square, that is sigma I square equal to sigma square into sigma I square equal to sigma square into xi the square, where sigma square is a constant. Then the steps are: first rank the observation according to the value of xi beginning with the lowest, then omit the central value, then group it into two then divide the whole observation into two groups, then run the regression, obtain the residuals, then attach the degrees of freedom, then find the lambda. The assumption of homoscedasticity, if ui are assumed to be normally distributed, the assumption of homoscedasticity is valid unless or if the computed lambda is equal to f is greater than the critical value at each chosen level of significance. The homoscedasticity is rejected and there is heteroscedasticity. This is about the Goldfeld quant test. Next test is the Bruch-Pagan-Godfrey test. Here we have already seen the Goldfeld quant test, but the success of the Goldfeld quant test depends not only on the value of c, that is number of central observation, but also on identifying the correct x variable with which to order the observation. This limitation of the test can be avoided if we consider the Bruch-Pagan-Godfrey test. Let us consider a k-variable regression model, that is y equal to beta 1 plus beta 2 x 2I plus beta kx ki plus ui. And assume that the error variance sigma I square is described as sigma I square is a function of alpha 1 plus alpha 2 z2t plus alpha m zm. Some or all of x can serve as zi. Specifically assume that sigma I square equal to alpha 1 plus alpha 2 z2I plus alpha m zi. Sigma I square is a linear form of zi. To test whether sigma I square is homoscedastic, test the hypothesis that alpha 2 equal to alpha 3 equal to alpha m equal to 0. If alpha 2 equal to alpha 3 equal to alpha m equal to 0, and then sigma I square equal to alpha 1, which is a constant. This is the idea behind the Bruch-Baget test. The steps of first estimate by OLS and obtain residual sum of squares u1 cap, u2 cap, etc. That is, here estimate this equation. This equation is estimated, that is k variable model. Then obtain the residuals u1 cap, u2 cap, u1 cap. Second one, obtain sigma cap square, that is equal to sigma ui cap square by n. Then third one, construct variable pi defined as pi equal to ui cap square divided by sigma cap square, which is simply each residual square divided by, that is ui cap square divided by sigma cap square. A regress pi thus constructed on zi's as pi equal to alpha 1 plus alpha 2 z2 plus alpha m zm plus vi, where vi is the error term. Then obtain the ESS, that is explain sum of squares from the above equation and define theta equal to 1 by 2 ESS. Assuming ui are normally distributed, one can show that if there is homoscedasticity and if the sample size n increases indefinitely, then theta tend to act the chi-square distribution with m-1 degrees of freedom. If in an application the computer chi-square exceeds the critical chi-square value at the chosen level of significance, one can reject the hypothesis of homoscedasticity. That is, there is heteroscedasticity. That is, if the computer value exceeds the critical chi-square value, there is heteroscedasticity. The next one is White's general heteroscedasticity test. That is, here, unlike the Gottfried-Kahn test, which requires the reordering the observation with respect to the x variables, that supposedly cause heteroscedasticity or BPG test, which is sensitive to the normality assumption. The general test of heteroscedasticity is proposed by White. It doesn't rely on normality assumption and is easy to be implemented. Here, it is a general test. Therefore, it is known as White's general test. In the Gottfried-Kahn test, we have seen that it requires the reordering of the observations. Then in BPG test, it is sensitive to the normality assumption, but it is not sensitive to the normality assumption and it is very easy to implement also. Here, for it can be explained as follows. Now consider the following three variable regression model, that is y equal to beta 1 plus beta 2 x2I plus beta 3 x3I plus ui. And White's test can be done as follows. Then this can be explained as follows. Consider the model y equal to beta 1 plus beta 2 x2I plus beta 3 x3I plus ui. The White's test can be done as follows. Step 1. Estimate the equation 1, that is this. Obtain the residual. Run the auxiliary regression. This is the second. The first step is estimate the equation, this equation, and obtain the residual ui cap. Run the auxiliary regression ui cap equal to alpha 1 plus alpha 2 x2I plus alpha 3 x3 plus alpha 4 x2I square plus alpha 3 x3I square plus then the interactive term. Obtain the squared residual sum of squared residuals from the original regression are regressed on original x value x3, x2I and x3I and their squared values and its cross product. And its higher powers can also be introduced. And here there is a constant term in this equation, even though the original regression may or may not contain it. Obtain the R square from this auxiliary regression and then Under the null hypothesis that there is no heteroscedasticity, it can be shown that the sample size n times the R-square obtained from the auxiliary regression asymptotically follows the chi-square distribution with the degrees of freedom, which is equal to the number of regresses in the auxiliary regression. That is, n into R square follows the chi-square distribution with degrees of freedom. Then in the next step, compare if the chi-square value obtained from this equation exceeds the critical value at the chosen level of significance, there is heteroscedasticity. If it does not exceed the critical chi-square value, there is no heteroscedasticity. This is the assumption. White's test can be a test of pure heteroscedasticity or specification error or both error. It has been argued that if no cross product terms are present in the White test procedure, then it is a test of pure heteroscedasticity. If the cross product terms are present, then it is a test of both heteroscedasticity and specification bias. That is, this White's heteroscedasticity can be used for testing the heteroscedasticity as well as the specification or the bias. If we use the cross product term, then we can test the heteroscedasticity as well as the specification bias. If the cross product term is not present, then we can test the heteroscedasticity only. The next test is the Koenig-Bassett test, the Koenig or KB test. It is based on the squared residual, that is UI cap square. But instead of being regressed on one or more regresses, the squared residuals are regressed on the squared estimated value of the regressant. That is, if the original model is yi equal to beta 1 plus beta 2 x2i plus beta 3 x3 plus beta k ski plus ui, that is a k variable model, then ui cap square equal to alpha plus alpha 2 yi cap square plus vi. Yi caps are the estimated values from the model 1. The null hypothesis is that alpha 2 equal to 0. Not rejected, there is no heteroscedasticity. The null hypothesis can be tested by the usual t-test. That is, ui cap is regressed on the estimated yi. First run this equation, obtain the error term, then obtain the estimated yi cap, then do the regression. Then if the null hypothesis is alpha 2 equal to 0, if it is not rejected, there is no heteroscedasticity. If rejected, there is heteroscedasticity. And its significance can be tested by the t-test or the f-test. If the model is in double log, then squared residuals are regressed on log yi cap square. It is applicable if the error term in the original model is not normally distributed. That is, this can be applied if the error term in the original model is not normally distributed. These are the various test method, that is Koenig-Bassett test, then White's general heteroscedasticity test, then Bruce-Packed and Gottfried test, then Gottfried test, Spearman-Rank correlation test, Glaser test, and Park test. Now let us see the remedial measures. When sigma I square is known, then use the method of weighted least square. When sigma I square is not known, we can use the consistent, that is White's heteroscedasticity, that is consistent variance standard error or the robust error term methods can be used. The weighted least square methods we have already discussed, and therefore now see what is the consistent variance and standard error or the robust error term method. Consider the model y equal to beta 1 plus beta 2 xi plus ui, and variance is ui equal to sigma I square, that is heteroscedastic variance, and variance of beta 2 equal to, as explained, sigma xi square sigma I square divided by sigma xi square the whole square. Since sigma I square is not directly observed, we use ui cap square, that is the residual gamma squares for each I in place of sigma square I. Since sigma square I square is not directly observable, use the ui cap square, that is residual sum of squares in the place of the sigma I square, that is the estimated variance of beta 2 cap equal to sigma xi square ui cap square divided by sigma xi square the whole square. White's procedures can be generalized to k-variable regression model, that is y equal to beta 1 plus beta 2 x2i plus beta 3 x3 plus beta k xqi plus ui. Variance of beta 1 cap equal to sigma wi square ui cap square divided by sigma wi square the whole square. These are the remedial method. This is about the heteroscedasticity problem. We explained the nature, causes, detection method and remedial measures.